Okay, so in this lesson, we're still working Unit 1314. This is Box C, and we're going to cover the chain rule, which is the latest in our series of rules for finding the derivatives of functions. And this is going to follow nicely from what we talked about in the last lesson, where we reviewed composition of functions. And what I said is what we were doing when we were doing composition of functions is we were sort of doing the opposite of composition. We were doing decomposition of functions. We wanted to take a complex function and think of it as the composition of two simpler functions. So the example that we went through was, one of the examples we looked at was if we had a function that was x squared plus 2, all of it squared. We thought to ourselves, hey, we can think of this as sort of an inner function in here. We'll call this one g at x, where g at x is x squared plus 2. Okay, so everything inside the brackets is sort of our one function. And then what we're doing to the stuff in the brackets is another function. So we're squaring those brackets. So our second function is going to be f at x equals x squared. And then we thought of h at x as the composition of those two functions. Or, so f at g of x, or f o g at x. Okay, the composition. This notation is probably the one that's most useful to us here. So we think of an inner function g at x that has been put inside of our outer function here, f at x. Okay? So what is the chain rule here? Well, as you probably guessed, it's a rule for finding the derivatives of functions that are compositions of two simpler functions. So let's just state the chain rule here. Chain rule. First, we have the caveat that if f and g, the two functions that we're dealing with, are differentiable, functions, okay, and h of x is the composition of these two, so we'll just write it as f at g of x, then how do we find the derivative h primed at x? The derivative of this h at x that we have here is going to be the derivative of that outer function, f primed, evaluated at g at x, okay, or the composition of g at x and the derivative of f at x, times the derivative of what's inside, or our inner function here. So times g primed at x. So if we can think of this function as f at g at x, then our derivative is f primed at g at x times g primed at x. Okay? And just like I used that somewhat simpler notation involving u's and v's when I was doing product rule and quotient rule, we can think of this as, let's say we've got a function f at x, which is g at u, okay, where u is a function of x. Then our derivative, f primed at x, is going to be g primed at u times u primed. Okay. So whatever is inside that function, we take the derivative of our outer function, multiply it by the derivative of that inner function. So for example, let's just draw a line here. The function that we were working with up above was f at x is x squared plus 2 all squared. Okay. Using that notation that I just introduced there, what is u? What is our inner function of x here? what is sort of the function that is sort of at the end of the composition of these two?
X squared plus 2.
Yeah, it's what is in the inside of these brackets here, x squared plus 2. And what is our outer function, or g at u? Yeah, x squared, or in this case we'll write it as u squared. Okay, so if u is x squared plus 2, what this function is it's taking u, or whatever is in the brackets, and it's squaring it. So we need the derivative of both of these things here. U primed is, well, the derivative there is 2x, and the derivative of u is 2u, just applying the power law. So now let's put this into this definition that we have here. F primed at x is going to be g primed at u times u primed. So what's g primed at u? Well, we figured that out. It was 2u. What is u primed? We figured that out. It was 2x. And now let's sub in, because we want this to be a function of x. We want f primed at x. Let's sub in what we know u is. Well, u is x squared plus 2. So we get 2 times x squared plus 2 times 2x. Or if we just clean this up a bit, 4x times x squared plus 2. And that would be our derivative. Okay. So to begin with, we will evaluate these using this definition that I've given you here in terms of g at u and u. And we'll do a couple of examples that way, and then I'll show you a little shortcut that can speed things up a little bit. Okay? That you can start using once you get good at it. Okay, so we've got 3 examples that we're going to go through here. Here's the first one. And for each of these 3 examples, the only instructions are find the derivative of the following functions. So here's our first one. F at x equals the square root of x squared plus 5x. And we want the derivative. Now, before we even set about trying to find the derivative, is there a way that we should rewrite this to make it a little easier to find the derivatives? What have we always done with square roots as we've been going along here? Yeah, we put it in exponential form. So this will be x squared plus 5x. And taking the square root is the same as having an exponent of 1/2. Okay. So now, let's take this function, f at x, and figure out what is u, what is our inner function, and what is g as a function of u. What are we doing to that, that inner part in there? So this one is a lot like the one that we just did. What is our inner function there? What is u? It's just going to be the x squared plus 5. That's that part that is inside the brackets there. And what are we doing to the x squared plus 5? Well, the x squared plus 5, we're taking the square root, or we're raising it to the exponent 1/2. So now we want u primed, and we want g primed. So we can take the derivative of both of these. Derivative of u here is just going to be 2x plus 5. And the derivative of g at u is going to be 1/2 u to the negative 3/2. Okay. Nothing surprising there. And now, let's put it all together, remembering that, thank you, negative 1/2, sorry. Because we have 1/2, we subtract 1, we get negative 1/2. So the definition of the derivative here was f primed at x is going to be g primed at u times u primed. So let's see. G primed at u is going to be 1/2 u to the negative 1/2. But let's sub in what u is here. U is x squared plus 5x. Okay. And then we're going to multiply this by u primed. Let's see, u primed is 2x plus 5. So this is all times 2x plus 5. And there's our derivative. And the only thing left to do is simplify this a little bit. Okay, clean this up. So what can we do to sort of rearrange this a bit? Yeah. Negative exponent here, it's going to go down in our denominator. So this is going to become the square root of x squared plus 5x down in our denominator. And up in the numerator, we're going to have, well, everything else, 1/2 2x plus 5. And one last thing we can do is, because this is 1/2 up in our numerator, we can rewrite this as 2x plus 5, and we can bring the 2 down into the denominator. Because 1/2 is just dividing this thing in brackets here by 2, so we can just divide by 2 down to the bottom. And we get x squared plus 5x. Okay? And there's our derivative. Okay. Fair enough? Good? Okay. Let's try another one here. Very similar. This time we'll do it using a little bit of a shortcut here. So you don't have to write out g at u and all that stuff. So we've got y equals 1 over square root of x squared plus 4. How can we clean this up a little bit so it's easier to work with the derivatives? What do you think? Yeah.
Negative 1/2.
Yeah. We've got square root down in the denominator, so we can have exponent of 1/2, but because it was in the denominator, we're going to have a negative exponent there. Okay. So now we know that we've done enough of these, I think, that this thing inside here is u, and sort of this something to the negative 1/2 is our g at u. Okay. So let's just jump right in and do our derivative here. Okay. So if I'm taking the derivative of g at u, I can sort of imagine that this thing that I have here is just a power function. So I've got an exponent up here. I'm going to take the derivative of it. I'm going to bring the exponent down out in front, negative 1/2. I'm going to keep what's inside the brackets the same. Okay, and I'm going to subtract 1 from my exponent. Okay, so I've taken that derivative of g just like I would anywhere using that power law. So this whole thing right here is g primed at u. And then I need to multiply this by u primed, which is the derivative of what is inside those brackets there. So inside the brackets, I've got x squared plus 4. Derivative is just going to be 2x. Okay. And there's my derivative. And then, of course, it's just a matter of cleaning it up. I've got 1/2 and a 2, so those are going to sort of cancel each other out. And I'm going to have negative x over x squared plus 4 to the power of 3 over 2. So that's cubed. And then we take the square root. Okay. And there's my derivative. Okay. All right. So a little bit shorter without writing out explicitly what all the functions are. So I would write it out explicitly to begin with, and then as you get good at it, you can shorten it up a little bit. Last example. G at x is 1 over 2 over x squared minus 3 over x all squared. Looks complicated. We're going to do it exactly the same way as we did the other ones. Okay. How can I rewrite it? Go for it.
2 over x squared minus 3 over x, brackets, negative.
Okay. So I can take that squared from the denominator, turn it into a negative exponent. I can make this even simpler, make it even easier to take derivatives of. Okay, I got a bunch of fractions inside that bracket, okay, with x's at the bottom. What can I do with those x's that are down at the bottom in the denominator? What do you think? Yeah, same thing. Same thing. I can take those exponents into negative exponents. 2x to the negative 2 minus 3x to the negative 1 all to the negative 2. Once I've got it like that, let's take our derivative. Okay, so this thing in brackets is u. The exponent here gives me g at u. Okay. So what is my derivative going to look like here? Well, let's bring down the negative 2. Keep the u in the brackets the same. 2x to the negative 2 minus 3x to the negative 1. Subtract 1 from our exponent there, and that gives us g primed at u. And then multiply it by the derivative of u inside the brackets there. So let's see. This is going to be negative 2 times 2 gives me negative 4 x to the negative 3 plus the negative 1 times negative 3 gives me plus 3 x to the negative 2. And that's my u primed. From here, it's just a matter of cleaning this up again. So let's see. What can we do? Well, we can take this thing with an exponent negative 3, bring that down into the denominator for sure. So 2x to the negative 2 minus 3x to the negative 1 all to the exponent 3. And then up in the numerator, we're going to have negative 2 times negative 4x to the negative 3 plus 3x to the negative 2. Now this is where the second thing that we talked about on Thursday comes in. We talked about composition of functions. We also talked about factoring more complicated expressions. What we're going to want to do is factor out the lowest power of x from our numerator. So I'll just say factor out lowest power of x. Why do we want to do this? Strictly speaking, I mean, this is a valid expression for a derivative. But think of the kinds of questions you've been asked to do in this course. It's always take the derivative, set it equal to 0, and solve for x. So if we've got something that looks like this, we set it equal to 0 and solve for x. We want where the numerator is going to be equal to 0. So we want to be able to factor that numerator to find the zeros. So that's why we go through this step of factoring out the numerator. Most cases, we don't care what happens in the denominator. So we're usually just going to leave the denominator as it is. Okay. So let's factor out our lowest power of x, which is x to the negative 3. So I factor out x to the negative 3, and I get negative 4 plus 3x. And down at the bottom here, I'm still going to have 2x to the negative 2 minus 3x to the negative 1 times 3. Okay? And I'm going to leave the denominator like that. in case they ask me to take a second derivative. And then in that case, it's already in the form that I wanted it. The last thing I could probably do, if I really wanted to, is I could take this x to the negative 3, and I could bring it down into the denominator as well. Okay, and get x cubed, 2x to the negative 2 minus 3x to the negative 1, all cubed. And then I would probably leave it like that. I mean, I could, if I wanted to, multiply the x cubed into each of these terms, because this is cubed and this is cubed. But I'd probably just leave it like that. Brody.
When I factored out the top, I factored in negative x to the power negative 3 because I didn't want the coefficient negative to then change anything if I were.
No, you could do that as well.
Just multiply the
Yeah.
negative.
Just, well, I would just, if you're just factoring out a negative here, just making it, you had 2 to the 4 minus 3x, like that, all divided by, what do I have here, x cubed, and all this mess to the 3, 2x to the negative 2 minus 3x to the negative. Okay, yeah, that's fine like that. Okay, I mean, either way, it's pretty simple to take that numerator and solve it for 0 at this point. Okay, so that's the chain rule. Yeah. What did I do? Oh, it should be a 3. Thanks.
You said x to the power.
I said x to the power 3 and I wrote x to the power of 2. There we go. X to the power of 3.